Hello, everyone. Welcome to today's Power Corner. I'm your host, Aalyia Shaukat, the editor-in-chief of Power Electronics News. Today, we're sitting with David Jauregui, co-founder and CTO of iDEAL Semiconductor, to talk about the company's SuperQ technology. Welcome, David. How are you doing today?
Doing well. Thank you for having me.
Thank you for being here. Well, I wanted to, talk about SuperQ a little bit more. From what I understand, you and iDEAL's other co-founder, Mark, made a deliberate decision to bet on silicon when the entire industry was basically doubling down on wide bandgap. I want to know what gave you the conviction that superjunction wasn't the ceiling for silicon.
Sure. I think that to start, superjunction isn't a fundamental limit. It's actually a specific method to charge compensate a drift region within a MOSFET. That drift region is what used to block voltage in traditional MOSFETs. And in superjunction structures, this is typically achieved by using these alternating PN pillars in a symmetrical fashion distributed across the entire structure. And what we observed was that this approach was reaching these diminishing returns over time, meaning that each new generation delivered smaller performance gains, while significantly increasing the cost of manufacture and complexity. And so really what we saw was that the technology node was unbalancing what we call the cost performance figure of merit. And so instead of changing the semiconductor material as was done with the wide bandgap technologies, we decided with SuperQ to go and look at an alternative way to move away from these bulk PN pillars and come up with a new way to charge compensate that drift region I spoke of earlier. And this allowed us to improve various key MOSFET parameters while maintaining that cost performance figure or merit. And what I mean by cost performance is that power is a necessary evil for all applications, right? But it's not the selling feature of the application. Your laptop, your phone, your watch and whatnot, those are the selling features. And so the attributes of power need to be well balanced. No point in having the world's highest performance MOSFET if it's going to cost 10 times more expensive than the industry can bear. Same time, you can't deliver the lowest cost MOSFET that has terrible performance. You have to deliver a technology node that delivers both on cost performance, and that cost performance premium that provides a overall benefit to the customer, that balance is critical for these customers. And so we sought out to keep that balance with SuperQ.
Gotcha. And thank you for that. So from what I understand, SuperQ uses a nanometer thin film inside thin and long or high aspect ratio trenches rather than the bulk P and N type pillars that you were describing. And those are in the RESURF superjunction MOSFETs, right? So the reduced surface field, right?
And whatnot, but yeah, go ahead.
Yeah. Yeah. Okay. So maybe you can describe that evolution in a little bit more detail from the HEXFET of the 90s, the popular RESURF superjunction MOSFETs, and where you are now with the SuperQ MOSFET.
Yeah, well, the evolution, a lot of the development involved this concern of the so-called 1D limit of silicon.
Yeah.
But to begin, that 1D limit applies to conventional MOSFETs like the HEXFET. That actually all changed in the mid 80s with the introduction of a bunch of technical papers on the concept of charge compensated structures.
Okay.
Further, that was then further changed when industry commercialized what they call the superjunction technology in the mid 90s. And so by the use of this charge compensated structures create this multi-dimensional depletion. That function of that charge compensation is what breaks this one-dimensional limit. And so technically silicon MOSFETs have broken this one-dimensional limit for at least 25 years. And so anyone that continues to use this 1D limit to justify their technology is doing so by manipulating the technical message in their favor. And so we're long past this 1D limit of silicon. And like I said, it's been a commercialized technology since the late 90s. And so SuperQ kind of built on that multi-dimensional depletion principle where we look at charge compensating in the drift region, but we do it in a way that eliminates these coarse PN pillars, and we create a more efficient way of charge compensating the structure while allowing us to deliver these performance improvements that are needed in power MOSFETs without unbalancing cost performance.
Okay. So maybe we could talk a little bit more in a little bit more detail on what you basically just described. So,
Yeah.
you know, what the SuperQ MOSFETs actually look like at the device level, what enables both a high blocking voltage and a low on resistance, and what physics and that multi-dimensional depletion that you were talking about, that allow the super thin high K dielectric layers to block such high voltages while only taking up, and I read this, 5% of the device structure. So you already answered that, so I'm not going to ask that question, but please
No,
please carry on.
to build on, so then what
Yeah.
else, what is it that's unique? And at a high level, I talked about, all MOSFETs have this, they rely on the depletion of the drift region for blocking.
Okay.
The drift region is what adds to the on resistance of a MOSFET. And the key to lowering the on resistance of a MOSFET while maintaining blocking, the blocking voltage requirement, is being able to efficiently deplete that drift region with the least amount of area. And so fundamentally, charge compensated devices rely on that lateral and vertical depletion. And for example, in that superjunction structure, the classical superjunction structure, which relies on this array of PN pillars symmetrically distributed across the device, in which this P pillar, which is part of the blocking function, it consumes half the conduction area. So basically, only half of the area for the conduction of current, which drives the RDS on, is used, and the other half in that structure is used for blocking only. And so in SuperQ, we also rely on lateral and vertical depletion, but we achieve charge balance using, like you said, this ultra thin high K dielectric material that's embedded in a trench. This allows us to create an asymmetrical structure, meaning we don't need to have the same width for blocking as we do for conduction. As a matter of fact, yeah,
Okay.
theoretically, we can get to our blocking function could be as small as 5%. Whereas we can reclaim the other 95%. Those are so-called the theoretical limits. But most importantly, this dielectric, it has a high dielectric field strength, so it can support the blocking voltage we need, and it only occupies a fraction of the device volume. And so the result is a more uniform electric field distribution and a more efficient use of the silicon area, which all of that directly translates into a lower on resistance for the same blocking voltage. Does that make sense?
Yeah. That was quite helpful. Thank you.
Okay.
Um, could I ask, could you apply the same device structure to a wide bandgap, material or transistor? Why choose silicon to start with?
Yeah, so the core principle of our SuperQ technology is, how do we block the highest amount of voltage with the least on resistance? That is fundamental for all power devices, no matter what materials they're made out of. So in principle, SuperQ can, and there are some white papers and some investigations that we've done ourselves that you can apply it to some wide bandgap technologies. But however, we chose to start with silicon because silicon continues to offer that well balance of cost, manufacturability, quality, reliability, and it does so for a very large portion of the market. So our goal wasn't just to improve on one parameter, but improve on all parameters associated with the cost performance of the device. And so, these parameters I talked about earlier, they're expected to be included as a performance metric of MOSFET, not just RDS on or switching. And so silicon still remains very competitive in that regard.
Gotcha. Thank you. That was helpful. So atomic layer deposition and high aspect ratio trench etching, right? These are things that, from what I understand, are used in CMOS and memory fabs, but they haven't been part of the discrete power device world. So how did iDEAL actually get access to those process capabilities and discover the know-how to apply them to power semiconductors?
Yeah, so our initial work was done in a university research fab, which gave us access to these advanced tools. But the key challenge wasn't access to the tools, but more adapting the processes to suit the need of a power MOSFET. We spent a lot of time making sure we develop a technology node that not only works in the research, environment, but that also could be commercialized. More importantly, that can be built by traditional CMOS wafer fabs in the industry. So the hard work was adapting these ideas and these concepts used in these sideline industries to fit and be commercialized in a power MOSFET that is needed for this industry.
It's interesting. How does SuperQ's figure of merit stack up against GaN HEMTs in the market on this in the same voltage class?
Well, if we purely focus on switching loss versus conduction loss, then yeah, SuperQ can be very competitive with GaN. And the reality is the systems require a lot more than just that. And in real systems, that's only part of the story. Designers care about robustness, they care about avalanche capability, DVDT and DIDT immunity, surge current capability, gate voltage robustness, meaning if you have gate spikes, will your gate survive? And high temperature reliability. So we tend to forget the importance of these other parameters because the industry at times only focuses on switching losses or conduction losses, or hey, I can go to high frequency. SuperQ, our approach here was to maintain the intrinsic advantages that silicon delivers in these areas while improving the overall efficiency and balancing the cost performance. But it's important to highlight the need of these robustness parameters because in many times MOSFETs are the fuse of the application, meaning they're usually the first thing to fail when something goes wrong, even if it's not the MOSFET's fault. And so many times the MOSFET has to be able to absorb these high stress events, and silicon continues to deliver on that robustness needed to be able to survive those events.
Thank you. Thank you very much. May I ask, well, what's next for the SuperQ line? Do you see any potential expansion, say, in terms of voltage rating?
Yeah, so our goal was to develop a platform that scales beyond a couple of voltage nodes. Right now we're focusing on voltage nodes as low as 60 volts, and we're looking as high as 1200 volts. So to be able to do that with one platform is quite extraordinary. I don't think there's anything in the industry out there that can do that, at least not in silicon. And so our goal is to make a general purpose platform that delivers MOSFETs for a variety of applications, motor drives, industrial power, automotive applications, Class D audio, AI. It doesn't really matter. Our goal is to make a more ideal MOSFET, a more perfect MOSFET for all industries to use.
Gotcha. Thank you, David. Last question here. So the power electronics industry has been shifting focus, I feel, from silicon for nearly a decade, right? The discussion seemed to be, superjunction cannot compete with wide bandgap, right? Rather than is superjunction the best architecture that silicon can support? Say SuperQ proves out at scale, do you think that this has disruptive implications, say, for wide bandgap?
Well, look, I don't think this is about one technology replacing the other, and each technology will find their place. Absolutely. People have debated silicon since the days of indium phosphide MOSFET or gallium arsenide MOSFETs.
Yeah.
But to say that silicon is completely dead is a misleading narrative. That is just not absolutely true at all. The real question is which technology delivers the best balance of cost performance for a given application. The technology node that continues to balance that cost performance equation will continue to have a leadership position in power MOSFETs. We at iDEAL, our core focus is improving cost performance as a priority for SuperQ as a technology. And so I think that, as the market grows and changes, being able to deliver on that metric is a key parameter.
Thank you. Thank you so much for your time, David. Do you have any final comments, anything I might have missed? Just let me know.
No, I think that, like I said just now, that the power industry is one where that it's a necessary evil, but it's drawn a lot of attention because it does consume energy. But the ideal solution or the ideal MOSFET is one that doesn't consume any energy, and that's our goal. Our goal is to make the world's best MOSFET.
Thank you very much, David, and thank you for your time. I'm very excited to see more of SuperQ.
No problem. Thank you for having me.